that coming up at all?
Yeah, we can see your slides now, Chris. Thank you.
Yes. Thank you, and thank you for the opportunity to present here today. It's quite timely that Lisa's been on from Geoscience Australia before me, because that provides a great segue. What we'll be showing is a lot of, if you like, level of granularity below what's been presented in the last year presentation, down to some actual applications and real life examples of where we're actually utilising some of those foundational type data sets that are out there, and building apps and certain applications off of them. So I'll try and keep things moving if my screen's going to work. Okay, what's happening here? It's not. All right, let me go there and try and find out how I can move this forward. And so basically I'll be covering some of the Geoscience Australia, Digital Earth Australia products, looking at some curation issues, looking at the application and utility of some of those derived products for environmental watering and biodiversity, and then looking at some water observations and water body data, and how we've been able to translate water occurrence extent into AHD, which is a height datum, and some relationships to groundwater, and then an example of basically some apps built on the Earth observation products as a result of the standards that are out there. So very quickly, in addition to national map that Lisa spoke about, Geoscience Australia also have a Digital Earth Australia product that's a large data cube going back to the 80s, standardized processing, high performance computing, and the ability to integrate and leverage additional data sets. This gives you an idea of some of those products. There's fractional cover, land cover, water observations, and the like. And in particular, as mentioned, I'll be focusing in on the Wetlands Insight tool, which is a tool that merges water observations, fractional cover, and tassel capped wetness to develop some unique products to provide insights and time series understanding for water bodies. So basically, as I mentioned, it's a tool that combines open water, water vegetation mixtures, bare ground, fractional cover into a stacked line plot with some references there. So taking a step back, this is largely some of the science and journal applications that have actually been derived off of this. So there's some links there if anyone's particularly interested in following up on those. But to walk you through some of the process, basically, as we start with a wetland polygon, we get fractional cover, we get the water observations, we get Landsats 5 through to 9 actually, and then basically through a whole series of routines and steps produce a stacked output which has wet, open water, green vegetation, dry vegetation, and bare soil. Looking firstly at the fractional cover data set, which is one of the DEA products as mentioned. It basically gives you greenness, non-green, bare, and we take that data set to give the permanent vegetation, dry vegetation, and non-photosynthetic bare ground, and then augment that with water from the water observations, and then tassel cap wetness. So this is some of the water observations data set, and for those that don't know Australia that well, especially inland, our waters in terms of occurrence highly ephemeral and dynamic, and so getting a handle on those is something that is certainly appreciated and required for improved management. This is then the tassel cap wetness, and a link there that actually gives you some of the specifics in terms of the algorithms used and the thresholds to determine the wetness component. Then looking at some of these, that's one of the actual examples. Here you see largely an area of dry veg, some less water, and then some green veg. We move across to here where you've actually got less water, and then we go across to here where you've got more bare ground, and then across to here where it's largely wet and inundated, and that's an example of one of those particular herd swamps. Just for a moment, if I get things working. Again, this is an example of the open water vegetation, and then the green dry type vegetation mix that's actually coming through on those. And so they all get synthesized and put into a standard stack line plot. An example of a lacustrine system, because we're dealing, as we mentioned, with wetlands, which is basically lakes. And what happens with the time series, looking at a lake, then moving through to a riverine system, and these don't get over. This is on a floodplain in the Murray River, and then basically what can come out of those, where you can see back in the earlier years some more frequent inundation that we've had through the actual millennium drought, and then some more frequent inundations since. And then a palestrine system, which basically doesn't have that much open water, but has a lot more greenness. And sometimes these suffer fires and things like this, which you can also pick up through this system. Now, we mentioned the application and utility. So just looking at that now, we've got, as I mentioned, two examples, one looking at environmental watering and one looking at biodiversity. And firstly, in the environmental watering, through this process here, it's possible to pick up that there wasn't any increase to overbank flows and open water, but we've got an increase in green vegetation that was in part due to an environmental watering. That's in the Riverland of South Australia at a Ramsar site called Banrock. We've got further upstream from there in the Riverland Charwilla Ramsar site. We unpacked that a bit further, where we actually augmented it with daily flows at the border, which were just upstream from the actual site, and you can see a reasonable correlation in terms of the red stream flows and the open water, which is then often open overbank flow. We then bring into that the actual date series for the Landsat imagery, and then also the environmental watering events that have been taking place, and we can then unpack that a bit further to see with 90-day aggregate daily rainfall, to see if rainfall is actually impacted on the response. And basically we've got a situation here where the 90-day rainfall is actually quite low. There's no overbank flows and higher discharge, but we've got a peak in the green, which is actually in this first instance the result of those environmental watering events that happened up here. Moving across to the biodiversity, where we've been spending a lot of time looking at this down at a fairly fine scale, and I'm talking 1 or 2 Landsat pixels at the lowest common denominator. This is a site in the Fleurieu Peninsula. This place is called Yundi Nature Conservancy. We're working with a landholder there. This was the site on peat swamps. This was in 1949. It gives you an idea of the actual. Whoops, sorry. Gives you an idea of the status of the vegetation back in 1949, a series of drains through the area, and this is basically all bare apart from one tree back down here in the south, but certainly no dominant peat vegetation. This was the area more recently where they've actually undertaken some treatment. This is a reference peat condition site and another fragmenty site, and as you can see, lots of change in land use between 49 and 2020. Moving along, as we mentioned, they undertook a rehabilitation program, which involved a burn, some mulching, then some re-wetting, and so then that was basically the situation in 2021. And to give you an idea of how these sites can respond to some TLC, that was a site basically 12 to 15 months later. Basically, that resilient seed bank of at least 30 years of monoculture of Phragmites was amazing, in that there's now 70 to 80 native species that have re-emerged naturally, and some additional selected endangered plantings from the Seed Conservation or Collection Centre from the Botanic Gardens that's enriching this area. That's the site in January 23. And that was it basically a few months ago, and it's well over 1.5 metres tall. What we've done is develop some low-cost lines of evidence using the fractional cover, spectral profiles, and NDVI to provide a line of evidence to the market of those interventions and management actions. This largely involves treatment sites and comparison sites that complement then low-cost photo points and ground transect surveys. To look at the fractional cover, this will give you an idea of the Phragmites that was in the Phragmites site I showed, of the treatment site, Phragmites right up to here, and then the reference site. And then what's actually happened since the reference site is actually now starting to parallel the treatment site is paralleling the reference site, and that's a simple line of evidence that provides that. well understood by landholders and basically well received to date by the market, but nothing official as such as yet. This then unpacks that a bit further in terms of the actual spectral profiles using Sentinel-2. Well, we've got similar routines that we can go with Landsat, so that goes back to the full Landsat stack as well. But basically what you can see here is that there's quite a difference in terms of the treatment site, which is the grey, as opposed to the reference site, which is the dotted. That was summer seasonal mean over 2020, same in 2021. The treatment came in that period after, and that's basically the response between the reference site and the treatment site in summer 2022, and then again in summer 2023, providing, as we mentioned, low-cost lines of evidence that farmers understand as well as the market. To give you another line of evidence with NDVIs, we can see here the green is actually the reference peat sedge swamp, the red and the blue, the red being the Phragmites infestation, the blue being the treatment. You can see where the intervention started and what's actually been picked up since, where the treatment differentiated from the actual Phragmites and now starts to parallel the reference site. So what's required with that? Obviously, when you're dealing down at very small areas, lots of curation and thresholds, but which is appropriate for smaller areas, but not practical if you're trying to batch fold thousands of polygons. And largely those anomalies and spikes that you see in the routines are due to cloud and or shadow. And so we're looking at some automated routines to look at automatically rather than manually removing those. However, they are relevant at times, especially when there's fire and or drainage of certain areas. So this is a small site that actually gives you a treatment site and a reference site of a landholder that just came on board in the last couple of weeks, and I'll take you through what we've done there. That gives you an idea of the reference site. As we mentioned, it's only 2 pixels. The treatment site is only 4 pixels. We've been able to take this through. That's the original product, if you like, that comes out of that WITS routine that Geoscience Australia have developed, and we basically enhanced and modified. But you'll see images such as this that you don't want in there. These ones, and others. We run those routines, and then you get an example that goes from here, which has got a lot of these spikes and things in it, as you can see. And then after curation, you can see it's a very clean image and a very strong signal from only 2 pixels. Now moving across, because I'm conscious of time, as we mentioned, looking at some of the standard products that of water observation and water bodies that Geoscience Australia also produce. We've got the water observation data set, which has got bit flags. We've unpacked that down at the individual bit flag level and get some deeper insights than the standard product that's available on the national map, if you like. And then Geoscience Australia also produced what they call a water body product, which is derived from the water observations, and as we mentioned, available on the standard layer on national map. That's what you get for this particular polygon here. We've taken those, and you can actually add a couple of polygons if you like. We've basically taken that data and had a bit more of a deep dive into it. So firstly, we looked at their polygons compared to what the state agencies use with their mapping, because they're not the same thing. The DEA ones are actually derived from the open water, whereas the state mapping is often wetland mapping that takes into account the emergent and surrounding vegetation. So we had a look and compared them and said, well, this is in real time coming off of the DEA in the green, whereas the state agency process data is in the blue, where they are actually, the water bodies are similar. The situation is you get a similar result. What we've done here is add in some controls so you can actually play with the thresholds in terms of, as we said, valid pixels, but also whether you actually then want to include water and cloud, water and shadow in your assessment pool, and the results that you get from that, which gives you some additional insights. This is the 2 different polygons. That's the state mapping. This is the product out of Digital Earth Australia, and as you'll see in these situations, they're actually quite different, and that's due, whereas the previous one, they were similar because the polygons were similar. So we've quantified that, unpacked it to try and work out what's going to be fit for purpose for some of the state agencies. The other thing we've done is, as we mentioned, is look at groundwater data and well data that's read live from the state agency. through basic web service and interoperability, and the bottom one, which is actually the water body data that can be read live straight off of Geoscience Australia. That's just it. On the side here, you've got percent of extent of inundation, and on the side here, you've got depth to groundwater. We merge those two together through some fancy algorithms, and we can create AHD from extent data and show the relationship, in this case, how this wetland has lost connectivity and is now turning into a terrestrial environment as opposed to an aquatic ecosystem. Then we have a whole series of dashboards and other metrics that we work with to provide additional insights. And that's just an example of some of those, and a few more examples of the relationship between the derived AHD. Other tools that we've developed is benchmarking, so you can actually pull up a handful of different wetlands and compare them over time. In this case, you can also see these ones which have actually lost connectivity, which is these ones down the bottom here, and this one over here, which is there, and that these ones over time going back to 1990 and then through to the last decade, nowhere near the significant changes that you've actually got in these ones that you've actually lost connectivity. And so that's all generated server side through basically analytics at the back end, and then just rendered through a browser on screen. A range of the actual products and attributes that we deal with. Again, you can stratify things to a user-defined season, run seasonal decomposition, and then generate some auto-generated narrative based on some business rules that you set up. And then that's the other thing that we've looked at is we've also got the prototype for the whole of Africa that provides you with a series of outputs at the polygon level as well. And that was, interactive notebooks, if anyone's interested in terms of what DEA have available through their sandbox. This is also available through DEA Africa. And that was largely it. Thank you very much.
Thanks very much, Chris. The thing that struck me there really was wetlands. They're quite transitionary, but you were able to show using the EO data that you can monitor them to a real high degree. And I did like the biodiversity monitoring that you were doing as well, only from a few pixels. I think that was brilliant. Okay, does anyone have any questions for Chris at all? No, can't see any hands. Okay, thank you very much, Chris. And good to see you. Good to see your work. Thank you very much indeed.